Welcome to Drone Systems and Control course. In the previous lecture, we talked about what is autonomy and automations, and we talked about one important task in autonomy is sense and avoid or collision avoidance. What are the different phases? In this lecture, we go in details into failures, fusion, verifications, and various other components of sense and avoid. Right? The lecture objective is we look at sensors, sensor fusion, verification. We will also look at sensor technology itself. What are the important parameters, uncertainties in type of sensors, what are the ranges it can be used, and what are the challenges. We will look at the trajectory prediction, linear worst case prediction, and we will also look at the decision algorithms. Now, moment I say a target, which we talked about in sense and avoid, target is an important aspect of it. For a drone, there are different targets being present, right? You could have a birds which can fly anywhere between 1,000 feet and above. You can have a migratory birds which can just fly at a higher altitudes. You can have a RC aircraft, right? Somebody is operating with human. It's not autonomous. It's a human operated. It could be flying anywhere between 400 feet. Higher it can go, but requires an approval. You have multi-rotor systems, usually operates up to 400 feet, right? It could be a human operated, it's not autonomous. You could have parachutes, you could have hot air balloons, you could have gliders, right? Very important if you look at parachutes, hot air balloon and power gliders, they may not have the ability to maneuver so easily, right? Then you could have helicopters. They are instrumented with all kind of sensors and everything, right? You can have light aircraft, military aircraft, cargo, UAS, everything could operate, right? All of this could be targets, right? That could appear in front of you, right? There are static targets which I am not talking of, that we will take into account when you go in details, right? Now, what is the important requirement when you talk about sense and avoid for a different category? I am classifying this into 4 categories. Category 1, the targets is not able to communicate. The target cannot make any actions, right? You are putting a hot air balloon. It has an instrument, but it cannot communicate, it cannot take any actions, right? You can think of a bird. It's a non-cooperative system. Okay? Category 2 targets, or they will not communicate, but they can initiate some actions. Right? I am just putting in VMC. VMC means visual meteorological condition. They will be able to make some actions. For example, RC model is there. I am flying, right? I see there is a collision. I will be able to take some action, right? And then move. Category 3, they can communicate and they can also take actions in visual meteorological conditions. Category 4, they communicate, they take actions, right? That will also comes into picture. Now, category 1 and 2 needs active sensor to detect them. Category 2, if you look at in a visual meteorological condition, is needed, right? So, sensors plays an important role. If you look at a category 3 and 4, to some extent, you can communicate with them and take an self-aware maneuver. Right? So, if you see the category 1 and 2 becomes very critical, because there is no way we can communicate, we do not know whether they can take any action or not, right? So, sensor plays an important role to navigate with them, right? Now, let us look at timelines in sense and avoid, right? A drone is flying, right? And another drone is coming here. I am looking at a desired separation needed is so much distance, right? Now, what is my challenge? My biggest problem is my uncertainty in sensing. Uncertainty in detecting the target, uncertainty detecting its position, velocity and geometry of it, all that going to play an important role in developing sense and avoid solution. Is that the only thing? No. We have many factors plays an important role. Initial detection. How far away I can detect him, I may take some time to declare whatever I detected as a valid threat, right? I declare the track itself because I'm able to see him. After some time I'm not able to see, so I will not call the continuous detection is required, so that I can declare as a valid track. Once I declare as a valid track, I need to declare them as a threat. Once I declare them as a threat, I may take some time to determine the action that I need to perform, and then I pass on the action to my flight controller, which will take some time to execute it. The time to compute this is also going to play a role. And sensing as the uncertainty influence all these stages. That's why the task of performing sense and avoid is a complex. Right? So time to detect and declare is one of the biggest challenge. Time to generate a feasible trajectory is another factor that I need to take into account. Time to execute. All these are the factors that I need to take into account when I am talking about sense and avoid. Now, what are the failure scenarios? In the whole process of initial detection, declaring valid track, declaring as a threat or determined action or command and execute in the phase, I may have to use a different sensors, right? They work at a different conditions. Not all sensors going to work in all conditions, right? No free lunch theorem, no single algorithm is suitable for all scenarios. That's going to be a biggest factor in failure, right? Threat is undetected. My sensor is not able to see that threat, or I am detecting the threat at very late. I may not have sufficient time to respond. I have detected the threat, right? I detected them early, but my calculation of the position of velocity at which the threat is moving is wrong. That will also cause a problem. All these are the important factors affecting your collision avoidance capability or sense and avoid capability, right? Now, what is the best way to do? I know there is an uncertainty, right? The best way to minimize the uncertainty, because detection of threat is an important aspect. I want to minimize as much as possible. I will not use single sensor. I may use a different number of sensors. When I say a sensor, each sensor will have different range, different field of view, different accuracy, different update rate. For example, camera can give you a 32 frames per second, whereas my radar can give me at 100 hertz, right? So I have a different update rates and they are at a different coordinates. I may have to do the coordinate transformation also, right? I have to take all these aspects into picture. I will do the fusion and tracking, right? Start the tracking. I will provide weighted sum of all this, right? And I align the estimates so that I can say the track is accurate. Once I have the track, I have a high probability detection, low false detection, accuracy. So the one way to do it is fusion. You see, in the beginning I mentioned autonomy, highest level of autonomy will increase the cost, right? Now you see, for a sense and avoid task, there is an uncertainty of sensing. The measurement uncertainty plays an important role. I want to minimize that. I wanted to reduce the risk. Safety is more important. Then I may have to add multiple sensors. Not just multiple sensors, my computational cost also going to increase to get high reliable detection, low false alarm and accuracy, right? So fusion can be done, but it will increase the cost and computational overhead, right? Now I have done all of this, but I need to do verification process before am I deploying it. So in the first lecture we talk about mathematical modeling of the drone, right? I model it either in MATLAB, I create a Simulink diagram, or UML, SysML, HDL, I have the modeling of the whole system. Why am I doing it? I want to describe the system completely. What I want a sense and avoid to be there. I want to analyze, right? I want to perform multiple simulation to verify in what scenarios the system will fail, right? So I am trying to look at this analysis of my avoidance algorithm, in what scenario it will fail to detect, in what are the scenarios it can operate safely, so that I may have to perform. Then I may have to synthesize the model that I have created in check in real time, right? I have to implement it to check whether my control design is efficient, or the component design and the timing parameters of whatever I have taken into account is sufficient to generate the trajectory and track the trajectory such that the drone avoids the collision and perform the maneuver in a reliable manner. That verification process is also very important before we deploy, right? What I do, I may have a model. It could be a MATLAB model, Simulink model, or it could be a gazebo model, or it could be a high fidelity model. I have to do that. I have to transform the model, and I have to generate a functions, right? Function models and performance model. What is the performance metrics that I am going to use to say it works reliability? I want to create those models also. Then I have a system level requirement, and then I have a specifications. Using the system level requirement and specification, I may do the sense and avoid architectural design, right? Based on my sensor specification, drone operating limits and specification, I have to design the architecture. Once I do the architecture, once I have the performance metrics, I may have to develop the design, control design approaches. All these should be sent to my simulation to verify. I have to abstract this functional requirement, right, and the context. I have to abstract and bring it here, and I have to generate the code and put it in hardware to verify, am I able to detect in real time, am I able to generate the trajectory in real time, right? Then only I can look at the deployment aspect of it. Okay. Now, what are the factors, external factors affects the verification process? I have sensor A, B, C. I am using all the sensors for surveillance processing, right? I am trying to surveillance here is to check whether there is a threat or not. All of them have to communicate their detection or the sensor information to your computer, where you detect the threat and declare, and you come up with the resolution decisions, right? Resolution decisions are basically a trajectory that need to be communicated from your computer to your actuators, so that the actuators can provide the variational thrust so that the aircraft maneuver, right? What is the biggest problem? Delay in processing all the information. Different sensors operates at the different sampling rate. The time stamping may be different. I may have to take that into picture. The biggest challenge comes in the flight dynamics, right? External disturbance. Suddenly there is a crosswind or headwind, right? All that do affect my aircraft. External disturbance plays an important role, right? So I have to take all those aspects of it. These are the factors influence my verification process or the uncertainty in my verification process. What is the typical flow that I will be looking at? I have an environment, I have sensors which is looking at the environment, and they send this measurement to my computer, where I try to detect by fusion so that I can do detection reliably. I can track them, I can evaluate whether they are potential threat or not. Moment I define them as a threat, what are the information I am looking for? Location of the threat, orientation of the threat, velocity of the threat. In addition to location, velocity and orientation, I need a geometry of the threat. I pass those information to the next block, that is avoidance block, which prioritizes the threat and it resolves the conflict. When I say it resolves the conflict, it generates a feasible trajectory. Basically a local path planning will take place. That local path will be sent to your flight controller. As we discussed in control system design, it's basically a trajectory following controller. This local path is your local trajectory. The aircraft will start following the local trajectory. It generates a control input which goes into vehicle. I have to keep monitoring the environment till my threat is not in place. Okay, this is the typical flow diagram used for sense and avoid task. Right? Now let's look at collision avoidance in a holistic sense to understand the taxonomy of collision avoidance, right, or sense and avoid. Right? Collision detection is one of the tasks. Resolution is also another task. Let's look at various aspects of it. What are the sensor technology needed? Just sensing alone is not sufficient, right? What are you trying to sense? You are trying to sense targets which could be cooperative or non-cooperative. Cooperative means I can use radio communication to talk to him, to understand his heading. I may need a data link to transmit the data between them, or I may need to use ADS-B or ASD kind of a data so that I can pass the trajectory to between us, we can manage. If I am looking at a non-cooperative targets, I may have to use radar or laser rangefinders to find out the relative distance. I may have to use a stereo camera. If I don't want laser rangefinder, I may have to use stereo camera, or I may have to use a moving camera, or I may have to use infrared camera if I am operating in a night conditions, and electro-optical cameras. Your sensors may be different. That all comes in sensor technology. Once you have sensor to detect the target, of course you need an algorithm to detect from the sensor it's a target or not, right? Once you do that, you need a very important component called trajectory prediction. I am keep detecting the target and continues to get the target location. I may have to predict the trajectory of the target. I can use nominal method, simple, I can put a straight line, or I can use a worst case method, or I can use a probabilistic sense, or I can use a flight plan exchange if it's a cooperative target. I can use that information to predict the trajectory. That alone is not sufficient. Based on the trajectory, I have to declare the target as a conflict or not, or as a threat or not. Conflict detection is the biggest challenge, right? I have to look at the dimension of the target. I can do it in 2D horizontal plane or 2D vertical plane, or I can do it in 3D plane, right? I have to define them. It's a conflict. Once you do the conflicts, then you have to go into conflict resolution part. Basically, you can use rule-based, game theory, or field methods, or geometric methods, or you can use numerical optimization. If you have multiple targets being present, instead of handling them one at a time, you can do simultaneously using multi-agent solution, or you can use combination of any methods to generate your resolution. Finally, you have to generate your trajectory, right? You could have a continuous trajectory, or you could have a discrete decisions. You can simply say turn left, turn right, or increase the speed or decrease the speed. You climb or descend. You can do any of this decision making also, right? So this is how different components being present. But from the perspective of sense and avoid, the sense part, detect, track and evaluate, takes care of the first three components of SAA system. And your decision making capability, that is avoidance part, takes care of the next two component of SAA. For this course, we are not going to look at cooperative targets, we are going to leave them out. We are going to only look at the non-cooperative targets. And I am not going to go through all the methods for trajectory prediction, conflict detection and conflict resolution. We will take at least one of the classical approaches and we will discuss how this can be implemented. Right? Now let's look at a sensor technology. You have various sensors being there, right? You can use electro-optical sensor, which is a camera. You can have a LiDAR or laser. radar or acoustic sensors, you can use any of them. Every sensor has its own coordinate system. They can provide a relative range or absolute altitude. If you look at an optical sensor, it can give you azimuth and elevation, whereas if you look at a LiDAR, it will give a relative range. Radar will give the range and bearing. Acoustic sensor will give a bearing. Remember, sensor have its own uncertainty on situation awareness. Now, what are the parameters for SAA? What is the sensor can detect, right? That depends on field of view, right? What is your field of view? You are talking about 60 degree or 90 degree, 120 degree or 360 degree, right? That's the field where I can detect my targets. Range, distance with high probability, right? How far I can detect the targets with the highest probability. That's very important parameter. Update rate, the interval between measurements. What is the frame rate? If you're talking about a camera, are you talking of 20 frame per second or 30 frame per second or 50 frame per second? What is the interval between measurements? That's very important, right? Accuracy, how accurately you can detect the target from a given sensor. That again depends on the algorithm that what you are implementing, right? Reliability, probability of detecting the same, right, in every time. That's very important, right? How reliable your sensor is. Accuracy versus reliability aspect of it we discussed when we talk about modeling and when we talk about different sensors in the early lecture, right? Then characteristics of the inner target, the distance, the orientation and the velocity. These are the things which is needed, right? Now if I look at, I have taken 3 sensors. One is the camera, that is what we call electro-optical or infrared, because we are talking about all-weather kind of a solution in the day-night operations. Electro-optical or IR, if you see, it can work for few kilometers, right? It will be able to measure the distance between the obstacle and the sensor with some crude representation. You can just put a bounding box around it, right? That's what I call as a representation. You can use LiDAR. Less than a kilometer, some LiDARs are about 200 meters, some military grade versions can go up to kilometers. Autonomous vehicles, ground vehicles which use about 300 meters is possible. So less than a kilometer I just given, right, in a broader sense. I can use a computer vision based approach, right. I am not talking about electro-optical and IR, I can use a normal low cost camera. But then my distance comes down significantly, less than 100 meters, right, 120 meters, depends on your resolution and field of view, right. I can detect and track those objects, right. There is a low cost option, there is a high cost option, depends on the speed of the vehicle, depends on the sensitivity of the environment. You may have to determine what sensor technology is suitable for your mission, right. Now let's look at the challenges present in individual sensor technology. If I take a radar, I will be able to detect multiple targets. I can decrease the estimation error significantly. I can reduce the measurement uncertainty, right. If I use LiDAR, I can improve the detection accuracy again. I can improve the spatial resolution, but I can also improve the estimation error. If I use a vision, computer vision with a small low cost camera, robustness to environmental condition I can handle, I can decrease the estimation error to some extent. If I do a electro-optical, it will be very robust to environmental condition, but again I will have issue with respect to uncertainty in estimation, right. The longer the distance, higher the probability of error, right. What are the biggest challenges when you are looking at all these sensors? Processing speed, how fast I can detect the threat, computational effort that I need, how much time I will take to detect with high reliability. That's also a factor comes into picture, right. Now Somehow I detected the target. I am detecting it continuously. What is more important? I need to predict the trajectory of the target, right? I need to know short term nominal trajectory. Next 1-2 seconds, what's going to happen? I can just simply use linear or a Kalman filter to get the nominal trajectory of these drones, right? I can just get the prediction like this. Or I want a worst case for a short period. What about the look ahead time? Let's say for 6 seconds, worst case prediction I need. Or I may go ahead with the probabilistic trajectory for a short period of time. I'm looking at a feasibility, right? I'm just saying that next 6 seconds, the drone could be anywhere here, right? We are talking about uncertainty here. I am not able to say precisely where he will be. It could be anywhere here. There are various methods again for trajectory prediction. One can use a statistical technique. Looking at the past time history, I can predict the future, right? I can use neural networks based approaches like recurrent neural networks or tap delay neural networks or memory neural networks. I can employ one of them to predict, or I can even use deep neural network. See, if there is a swarm of birds coming in, right? The very interesting aspect is it's not just one person. Their collective behavior is very important. We may have to look at how they are interconnected, how one's decision influences the others. It's very important. In such scenario, you may have to look at graph neural network based approaches to predict the trajectory. Again, I am looking at short term trajectory. I don't want a long term. I don't want to know next 1 hour. I just need for next 6 seconds. It's more than sufficient. I'm looking at my local planner. I'm not looking at my global planning. Okay. Now conflict, right? Now what is conflict? I need to process whatever the object I have detected, whatever the geometry I have detected. With that, I need to process to identify 2 or more objects present in the environment can come dangerously close, right? So which means I need to determine when they will come close to each other. This is very important to take care from the point of view of safety, integrity of the drones, right? It is essential for real-time navigation and obstacle avoidance, and it prevents damage to the individual drone or the payload it carries, or it also to the environment in which it is present. What we need to determine the collision volume. Basically, I need to determine region around the drone representing the space wherever I am detecting the target. If another objects enter into the zone, that's what I need to determine. That's a collision volume. What is a volume in which, volume space in which these two can be present. You see, a detection has its own uncertainty. Continued detection for a few frames has its own uncertainty. Those sensor uncertainty along with algorithm processing uncertainty combines to give you a worst case probabilistic scenario. That itself is a volume space where he could be present, right? In that volume space, your uncertainty of your own sensors present in the drone, where you will be in that volume space to determine in a future time instant to identify how close 2 of us going to be, right? That's the biggest challenge, right? Then we need to define a threshold. What is the limit? What is the minimum separation distance that I am looking for? You remember in the previous lecture I talked about what is the minimum separation distance. Again, depends on how much time I am going to take, right? When I come closer to that separation distance, I have to do the maneuver very fast, or how much time I really need so that I can compute trajectory and look at the feasibility of the trajectory and pass on to my flight controller, right? So this definition depends on your sensor, right? Your dynamics of it. We have to take all that into picture and define a minimum distance or minimum time to collision. Right? Let's look at the two drones. Drone 1 is flying. It sees the drone 2 in the zone, detecting it. Right? Continuously I am detecting it and observe that it could be a potential collision for me. Same way, drone 2 detects drone 1 as a potential collision. So they estimate the trajectory. Right? And then this is the geometry that I am giving. I am giving a minimum separable distance. I talked about earlier, there is uncertainty that we need to take into picture, and based on that we give some space. Right? So this is the volume space I am talking of in 2D. Right? I am projecting it, and I am projecting this is my trajectory. Then I am saying the region of intersection of both these 2D space, and this is my region where potential collision can take place, or this is my conflict region. I want to avoid this conflict region. I need to generate a trajectory in such that I can avoid this conflict region. Right? So what I am trying to determine? I am trying to determine what's my time to conflict. Right? What is the position of the obstacle? Position of the drone divided by the relative velocity will give me a time to conflict. Assuming that during the process the drone as well as obstacle continue to travel in the same heading. Right? If they change the heading, then it will be difficult. Where is the position of conflict? My drone's position, my velocity into time of conflict will just determine what is the zone of conflict. Right? I can compute these two information. With that I can decide what should be my trajectory such that I can avoid the conflict zone. Right? Now I have solved the problem of detection. I solved the problem of conflict zone identification and the location and the time of conflict and everything. What is another important aspect is decision making. Right? I could have a simple decisions. Whenever I have a conflict zone, turn left or turn right based on where the obstacle being present with respect to my context. Right? Or I can move ahead with go up or go down. Right? You can have a discrete decision making capability too. Or you can generate a continuous trajectory and follow it. Right? Simple rule based approaches is also possible. You can have a deterministic method, you have a geometry based methods, you have multi-agent based methods, you have field methods like artificial potential field methods. You also have a game theoretic approach. See, what is more important is we are taking action. In the real scenario, both the obstacle as well as the drone will take actions together. It will be reactive. Right? Birds will also take its own actions. If it does, then what will I do? If those are not going to take action, they are non-cooperative, they just go what they want to do, right? Then how are you going to respond? Right? So we need to take those aspects also into picture when we are talking about decision making and path planning approaches. Right? In a summary, this particular course, this particular lecture introduces various sensor technologies. What are the parameters that is present in this technology, how useful they are? What is the detectability? How the reliability is a factors that we need to take into account. In determining thrust, can we have a general structure which can handle the diversity which is being present? Then we talked about decision making capability, partially observable scenario or uncertainty in detection. What happens suddenly targets start popping up? What will I do? Can I be fault tolerant? Can I handle those by adding a multi-sensor fusion? Right? We talked about general SAA architecture, right? HA process, how the time of detection, trajectory prediction, conflict identification, all that will influence. We discussed about all of that, right? Now, suppose we have the threat, right? And the geometry is determined, the position is determined, and velocity is determined with certainty. What shall we do? That's what we are going to look at in the next lecture, right? Once we have the local path planning generated, we will discuss about how do we do the detection and how do we do the trajectory predictions and all that, right? So very important component in the whole lecture is how do we generate the path, feasible path, such that the drone avoids the collision and escape the conflict zone, right? Thank you.